When we sent a spacecraft to explore Saturn and its moons, we discovered something extraordinary happening at one of the smallest worlds in that distant system. From the frozen surface of a moon called Enceladus, water is shooting into space through cracks in the ice, rising hundreds of kilometers above the surface in ghostly white plumes. The setting is otherworldly, a tiny moon no larger than Arizona, orbiting a giant ringed planet in the cold outer reaches of our solar system. Yet from its south pole, jets of water, ice, and vapor erupt continuously into the blackness of space. A phenomenon that changed everything we thought we knew about this small, frozen world. The surface of Enceladus is among the whitest and brightest in the solar system, covered in fresh ice that reflects nearly all the sunlight that reaches it. The terrain at the South Pole is cracked and fractured, with long parallel fissures cutting through the ice like wounds in the frozen landscape. From these fissures, the plumes rise, visible against the darkness of space when the moon passes in front of the sun or is illuminated from behind. The spray catches the distant sunlight, appearing as delicate white fans spreading upward and outward from the frozen surface below. You are listening to the Drowsy Astronaut, and tonight we are journeying to this remarkable moon to explore the water that shoots from its surface into the void of space. There is no rush in what follows, only the gentle unfolding of one of the most surprising discoveries in the exploration of our solar system. If you enjoy falling asleep to real science explained calmly and warmly, consider liking this video or subscribing for future journeys to distant worlds. Feel free to share in the comments where you are listening from tonight, what corner of Earth you occupy as we contemplate this distant frozen moon together. The plumes of Enceladus rise from the south polar region in over 100 individual jets, each one a fountain of ice and vapor escaping from beneath the frozen surface. Some jets are more powerful than others, producing thick sprays of material that climb high above the moon before spreading and dispersing into space. Other jets are gentler, creating softer wisps that barely rise before the material begins to fall back or drift away from the tiny moon's weak gravity. Together, these jets create the appearance of a continuous spray, a perpetual exhale of water from a world that should, by all expectations, be frozen solid and geologically dead. The material in the plumes is primarily water, existing as both vapor and tiny ice crystals that form when the vapor meets the extreme cold of space. Each ice crystal is incredibly small, typically about 1 micrometer in diameter, roughly 1/100th the width of a human hair drifting in the spray. These microscopic ice grains catch light beautifully when illuminated from behind, creating the ghostly glow that makes the plumes visible in spacecraft photographs. The spray is delicate, almost ethereal in appearance, yet it represents an enormous amount of material escaping continuously from beneath the ice. Every second, approximately 200 kilograms of material leaves Enceladus through these plumes, shooting upward through the fractured ice and into space beyond. Over time, this adds up to a substantial loss of material from the moon, though Enceladus has been erupting for so long that the process clearly sustains itself somehow. Some of the spray falls back to the surface as snow, coating the terrain near the vents in fresh ice that keeps the south polar region looking young. Other material escapes the moon entirely, drifting into orbit around Saturn, where it contributes to structures we will explore later. The height of the plumes varies depending on which jet we observe and how active it happens to be at any given moment. Some material rises only tens of kilometers before falling back, barely escaping the fractures from which it emerged into the cold vacuum above. Other jets produce sprays that climb hundreds of kilometers, towering above the small moon like impossibly tall fountains in the darkness of space. The most energetic eruptions can send material nearly 500 kilometers above the surface, higher than the orbit of the International Space Station above Earth. The appearance of the plumes changes depending on the viewing angle and the lighting conditions when spacecraft cameras capture images of the eruptions in progress. When viewed from directly above, the jets appear as bright spots scattered across the south polar terrain, each one marking a source point for the escaping material. When viewed from the side, with the sun behind them, the plumes appear as delicate fans of white spray rising from the curved horizon of the small moon. The most dramatic images show the plumes silhouetted against Saturn or against the blackness of space, their feathery structure clearly visible against the dark background. The temperature of the material in the plumes is far warmer than the surrounding surface ice, though still extremely cold by human standards. The spray emerges at temperatures around -90 degrees Celsius, which sounds impossibly frigid, but is actually much warmer than most of Enceladus's surface. The surrounding ice sits at around -200 degrees Celsius, cold enough that the warmth of the plumes represents a significant temperature difference. This relative warmth tells us that the material comes from somewhere warmer than the surface, from deep inside the moon, where conditions are different. The continuous nature of the plumes distinguishes them from eruptions we might see on Earth, where geysers like Old Faithful erupt periodically and then pause. The plumes of Enceladus do not seem to turn off, maintaining their spray continuously year after year across all the observations we have made. The strength of individual jets may vary over time, with some becoming more active while others quiet down, but the overall eruption never stops. Enceladus is perpetually exhaling, constantly shooting water into space, in a process that has likely continued for millions of years. The source of this water is not the surface ice itself, but rather a vast ocean of liquid water that exists beneath the frozen crust. The plumes represent a connection between this hidden ocean and the space above, material from the subsurface sea finding its way through fractures in the ice and escaping into the void. This makes the plumes remarkable, not just as a visual phenomenon, but as a window into what lies beneath. Samples of an alien ocean shooting into space, where spacecraft can collect and analyze them. The water falling as snow on the south polar terrain once flowed in darkness beneath kilometers of ice. The spray contains more than just water, carrying along traces of other materials dissolved or suspended in the liquid from which it originates. These additional substances, salts, organic compounds, tiny particles of rock, tell us about the conditions in the ocean below and the processes occurring there. The plumes are messengers, carrying information from a hidden world that we cannot see directly up into space, where our instruments can study it. Each ice crystal in the spray is a tiny capsule containing secrets about the dark waters of Enceladus. The location of the plumes exclusively at the South Pole reflects something special about this region of the moon that makes it more geologically active. The ice shell is thinner here than elsewhere on Enceladus, perhaps only 20 to 25 kilometers thick, compared to much thicker ice at other latitudes. The thinness of the ice allows heat from below to escape more readily, and fractures in the thin crust provide pathways for material to reach the surface. The South Pole is a window into the interior, the one place where the hidden ocean can communicate with the universe beyond. The weak gravity of Enceladus plays a role in allowing the plumes to rise so high and for so much material to escape entirely into space. A moon this small, only about 500 kilometers across, has very little gravitational pull, making it relatively easy for spray to achieve escape velocity. On a larger world with stronger gravity, similar eruptions might produce only modest geysers that quickly fell back to the surface. On Enceladus, the same energy produces towering plumes that can send material out of the moon's gravitational grasp entirely. The visual beauty of the plumes has captured public imagination since their discovery. Images of the spray becoming iconic representations of the active outer solar system. The photographs show something that should not exist, according to our old understanding. A tiny frozen moon, far from the sun, actively erupting with water. The delicate white fans rising from the ice challenge our assumptions about what is possible in the cold outer reaches of our cosmic neighborhood. Enceladus refuses to be the dead, frozen world we expected it to be. The plumes also create practical opportunities for exploration that exist nowhere else in the outer solar system in quite the same way. If we want to sample the ocean of Enceladus, we do not need to land on the surface or drill through kilometers of ice. We can simply fly through the plumes, allowing the spray to pass through our instruments, collecting material that came from the ocean below. A spacecraft passing through these eruptions can sample an alien ocean without ever touching down, gathering data about conditions hidden beneath the ice. The continuous eruption of the plumes means they will likely still be active whenever we choose to send future spacecraft to investigate them more closely. Unlike volcanic eruptions on Earth that might end before a mission arrives, the plumes of Enceladus have demonstrated stability across the entire period we have observed them. Scientists planning future missions can count on the plumes being there, ready to provide samples of the ocean below to whatever instruments we send to collect them. The perpetual nature of the eruptions makes Enceladus an inviting target for exploration. The material escaping from Enceladus does not simply drift away randomly into the Saturn system, but follows paths determined by orbital mechanics and the moon's motion. Some escaping particles enter orbit around Saturn, joining a vast diffuse ring that Enceladus continuously maintains through its eruptions. Other particles may eventually be swept up by Saturn itself, or by other moons sharing similar orbital regions. The plumes connect Enceladus to the larger Saturn system, spreading the moon's substance across millions of kilometers of space. The discovery of these plumes transformed Enceladus from a minor moon of Saturn into one of the most scientifically important objects in the entire solar system. Before the plumes were found, Enceladus was just one of many icy moons. Interesting, but not particularly remarkable among the dozens of satellites orbiting the ringed planet. After the discovery, everything changed. This small world suddenly became a priority target for astrobiology, a place where conditions might be right for life. The plumes elevated Enceladus to the top of the list of places we want to explore. The white spray rising from the South Pole continues erupting right now, as it has for millions of years, whether or not any spacecraft or any eyes are there to observe it. The jets shoot upward in silence, carrying their cargo of ice and vapor and dissolved substances from the hidden ocean into the cold darkness of space. Some of that material falls back as snow, adding to the fresh white coating of the south polar terrain, while other material escapes to join the structures orbiting Saturn beyond. The plumes are perpetual, patient, and profoundly mysterious. The discovery of these remarkable plumes came through the patient observations of a spacecraft that had traveled nearly 1 billion miles from Earth to study the Saturn system in detail over many years of exploration. The Cassini spacecraft arrived at Saturn on the 1st of July 2004, beginning a mission that would last over 13 years and transform our understanding of the ringed planet and its many moons. The spacecraft had traveled for nearly 7 years to reach this distant world, crossing the vast gulf of space that separates the inner solar system from the cold outer reaches. Upon arrival, Cassini began a systematic survey of everything in the Saturn system: the planet itself, its magnificent rings, and the diverse collection of moons that orbit within its gravitational domain. Among those moons was Enceladus, a small bright world that would eventually become one of the mission's most important discoveries. In the early observations, Enceladus appeared as a fascinating but not particularly unusual icy moon, one of many frozen worlds in Saturn's retinue. The surface was remarkably bright, reflecting nearly all the sunlight that struck it, suggesting the ice was fresh and constantly renewed by some process. The moon was small, only about 500 kilometers across, which according to conventional understanding meant it should have cooled long ago and frozen completely solid. Nothing in those early images suggested the extraordinary activity that would soon reveal itself. The first hints of something unusual came not from images, but from measurements of particles and fields around the moon. During close flyby encounters, instruments detected an unexpectedly dense cloud of water vapor and ice particles surrounding Enceladus, far more material than a cold, dead moon should produce. The magnetic field showed disturbances that suggested an atmosphere or outgassing that had no apparent source on the frozen surface, visible in photographs. Something was happening at Enceladus that did not fit the expected picture of a small, inactive ice world. The breakthrough came in 2005 when Cassini passed close to Enceladus with its instruments pointed toward the south polar region, in geometries that allowed detection of the plumes. Images taken with the sun behind the moon revealed the dramatic sprays of material rising from the surface, the ghostly white fans that would become iconic representations of this remarkable world. The plumes were not subtle. They were clearly visible once the lighting conditions allowed their detection. Unmistakable evidence of active geological processes on a moon that should have been geologically dead. The discovery surprised even the scientists who had designed the mission. The initial detection raised immediate questions about what could possibly be producing such activity on such a small, cold world. Enceladus was far too small to retain internal heat from its formation the way larger planets do, and there was no obvious energy source to drive geological activity. The surface showed no volcanoes, no obvious heat sources, nothing that would explain water erupting into space in such dramatic fashion. The plumes demanded an explanation, and finding that explanation became one of Cassini's primary objectives for the remainder of its mission. Subsequent flybys were designed specifically to study the plumes and understand their nature, with Cassini's trajectory adjusted to pass closer to the South Polar region where the eruptions were occurring. Each pass brought new information about the composition of the spray, the temperature of the source regions, the variability of the jets over time. The mission team realized they had stumbled upon something extraordinary, a discovery that would reshape the scientific priorities of the entire mission. Enceladus, once just one moon among many, became a primary focus. The imaging team captured the plumes from various angles and in various lighting conditions, building up a comprehensive picture of their structure and behavior. Some images showed the plumes in exquisite detail, individual jets visible as distinct sprays rising from specific points on the surface below. Other images captured the overall spray against the blackness of space, revealing the full extent of the material erupting from the South Polar region. Each photograph added to the growing understanding of this unexpected phenomenon. The discovery timeline unfolded over months and years as different instruments contributed their pieces to the puzzle of what was happening at Enceladus. The initial visual detection was followed by spectroscopic analysis, confirming the presence of water, then by measurements of heat emanating from the source regions, then by compositional analysis of particles captured from the plumes. Each new measurement confirmed and expanded the initial discovery, building a comprehensive picture of an actively erupting moon, harboring liquid water beneath its frozen surface. The scientific community responded to the discovery with excitement tempered by the caution that accompanies any unexpected finding that challenges existing understanding. Papers were published proposing various mechanisms that might explain the plumes, from purely geological processes to the presence of a subsurface ocean to even more exotic possibilities. Debates arose about the implications of the discovery, what it meant for the moon's history and potential habitability. The plumes became one of the most discussed topics in planetary science. The mission team recognized that the discovery warranted additional investigation, and Cassini's trajectory was modified to include more close encounters with Enceladus than originally planned. Each flyby was designed to address specific questions about the source of the plumes, about what lay beneath the ice, about the composition of the erupting material. The spacecraft returned again and again to this small moon, each pass revealing new details about the extraordinary activity occurring at its south pole. The reaction among the public mirrored the scientific excitement, with images of the plumes appearing in news coverage and popular science publications worldwide. A small moon of Saturn was shooting water into space. This was exactly the kind of discovery that captured imagination and reminded people of why space exploration matters. The visual drama of the plumes, their ghostly appearance against the darkness of space, made them accessible and memorable even to those without scientific background. The timing of the discovery was fortunate, occurring early enough in Cassini's extended mission that many years remained for follow-up investigation. Had the plumes been discovered late in the mission, there would have been limited opportunity to study them further. Instead, Cassini had more than a decade remaining to investigate Enceladus, designing and executing numerous encounters specifically tailored to understanding the plumes and their source. The discovery shaped the entire second half of the mission. The technology aboard Cassini, though designed and built years before the plume discovery, proved remarkably well suited to studying this unexpected phenomenon. The mass spectrometer could analyze particles captured from the spray, determining their composition in detail. The infrared instruments could measure heat from the source regions, mapping the temperature variations along the fractures from which the plumes emerged. The cameras could capture images in various wavelengths, revealing structure invisible to ordinary observation. The spacecraft was equipped for a discovery its designers had never anticipated. The confirmation that the plumes originated from a subsurface ocean, rather than from some other source, came through multiple lines of evidence accumulated over years of observation. The composition of the spray included salts and other materials that could only come from liquid water in contact with rock, not from surface ice alone. The heat signatures along the fractures indicated warmth from below, not from surface processes. The wobble of the moon as it orbited Saturn revealed that its interior was partially liquid, inconsistent with a frozen solid interior. The pieces fit together into a coherent picture. The Plume discovery at Enceladus changed the priorities of planetary science more broadly, elevating the importance of ocean worlds throughout the solar system. If Enceladus could harbor a liquid ocean beneath its ice, other moons might as well. Europa at Jupiter, Titan also at Saturn, perhaps others we have not yet studied in detail. The discovery expanded the potential habitat for life beyond the traditional focus on Mars and other places where liquid water might exist. On surfaces, oceans beneath ice became a new frontier. The personal reactions of mission scientists to the discovery often included elements of wonder and disbelief, the kind of emotional response that accompanies truly unexpected findings. Team members describe seeing the first clear images of the plumes and struggling to accept what they were seeing. Water erupting into space from a tiny frozen moon. The discovery reminded them why they had dedicated their careers to space exploration. The possibility of finding something genuinely new and surprising. Science is a human endeavor, and discoveries carry emotional weight. The years following the initial discovery brought continuous refinement of our understanding, each observation adding detail to the picture of what was happening at Enceladus. The jets were mapped and counted. Over 100 individual sources identified along the fractures at the South Pole. The composition of the spray was analyzed in increasing detail, revealing organic compounds and other materials that raised tantalizing possibilities. The behavior of the plumes was monitored over time, showing variations that correlated with the moon's orbital position around Saturn. The discovery process at Enceladus illustrates how exploration works at its best. A spacecraft sent to study one set of questions, finding answers to questions nobody had thought to ask. The Cassini mission was designed to study Saturn and its rings and moons in general, not specifically to search for active eruptions or subsurface oceans. The plumes revealed themselves because the spacecraft was there to see them. Patient observation rewarded with unexpected discovery. This is why we explore. The source of the plumes lies in specific fractures at the South Pole, long parallel cracks in the ice that scientists have nicknamed the tiger stripes for their distinctive appearance in images of the region. The tiger stripes of Enceladus are 4 roughly parallel fractures that cut across the South Polar region, each one stretching approximately 130 kilometers in length. They earned their nickname from the way they appear in images, dark stripes against the brighter ice, resembling the markings on a tiger's coat. The fractures are named Alexandria, Cairo, Baghdad, and Damascus Sulci, borrowing the names of ancient cities for these ancient wounds in the ice of a distant moon. Each stripe is a fracture zone, a place where the ice shell has cracked open and where material from below can reach the surface. The tiger stripes are spaced roughly 35 kilometers apart, creating a distinctive pattern that dominates the south polar terrain of Enceladus. They run roughly parallel to each other, though with some variation and curvature, cutting through ice that shows less cratering than other regions of the Moon. The youth of this terrain is evident from the relative absence of impact craters, suggesting the surface is constantly being renewed by fresh material deposited from the plumes. The ice near the tiger stripes is among the youngest on Enceladus. The width of each tiger stripe is substantial, roughly 2 kilometers across, representing not a simple crack, but a complex fracture zone with walls and ridges and detailed structure. The fractures cut through the ice shell of the Moon, creating channels that connect the surface to whatever lies beneath. Along the length of each stripe, the appearance varies, with some sections appearing more prominent while others are less distinct. The stripes are features of considerable scale, visible from great distances when lighting conditions are favorable. The warmth emanating from the tiger stripes distinguishes them dramatically from the surrounding ice, heat escaping from below along these fracture zones. The average temperature of Enceladus's surface is about -200 degrees Celsius, cold enough that nitrogen would freeze solid if it were present. The tiger stripes are remarkably warmer, reaching temperatures around -90 degrees Celsius, a difference of over 100 degrees from the surrounding terrain. This warmth represents heat flowing from the interior, escaping through the fractures where the ice shell is broken. The individual jets that make up the plumes emerge from specific points along the tiger stripes, concentrated at the locations where the fractures are most open and where heat is escaping most efficiently. Over 100 individual jet sources have been identified along the combined length of the 4 tiger stripes, each one a small vent through which material escapes. Some jets emerge from the central portions of the fractures, while others appear along the edges or at the intersection of fractures with other features. The distribution of jets tells us something about the structure of the fracture system below. The heat detected along the tiger stripes is substantial, far more than a small cold moon should be producing, according to simple models of planetary cooling. The total heat flow from the south polar region amounts to roughly 15 billion watts, enough to power a small country if it could be harnessed. This heat represents energy flowing from the interior of Enceladus, energy that must be generated by some ongoing process, rather than simply left over from the moon's formation. The tiger stripes are outlets for this internal heat. The relationship between the warmth and the jets is direct. The jets emerge where the heat is greatest, and both are concentrated along the tiger stripes, where fractures provide pathways through the ice. The warm material rising from below carries the heat with it, warming the ice along the fracture walls and eventually escaping into space as the plumes we observe. The tiger stripes are both heat vents and water vents, outlets for the energy and the material generated in the moon's interior. The terrain surrounding the tiger stripes shows evidence of resurfacing by material falling from the plumes, fresh ice deposited on older terrain in an ongoing process of renewal. Snow falls continuously here, not water snow as on Earth, but ice crystals falling from the spray above, coating the landscape in fresh white material. This continuous deposition fills craters, smooths terrain, and keeps the South Polar region looking young compared to the more heavily cratered regions elsewhere on the Moon. The tiger stripes are not just sources, but also causes of the young terrain around them. The structure of each tiger stripe suggests ongoing activity, with evidence of material flowing along the fractures and collecting at certain points before erupting. The walls of the fractures show ridges and textures that indicate complex processes occurring below, not a simple static crack, but a dynamic system. Some sections of the tiger stripes appear more active than others at any given time, with the distribution of activity varying over timescales of years. The fractures are living features, changing and evolving as the eruptions continue. The depth of the tiger stripes has been estimated through various observations and models, with the fractures likely penetrating through the entire ice shell in at least some locations. In places where the ice shell is thinnest, perhaps 20 to 25 kilometers thick, the fractures may provide relatively direct pathways from the ocean below to the surface above. The connection to the ocean is what makes the tiger stripes so important. They are windows into the hidden sea, channels through which ocean water can reach space. The opening and closing of the tiger stripes is thought to be controlled by tidal forces. As Enceladus orbits Saturn, the fractures widening and narrowing in rhythm with the Moon's orbital motion. When the fractures are wider, more material can escape, and the plumes are more intense. When the fractures are narrower, the flow is restricted, and the plumes are weaker. This tidal pumping connects the activity we observe to the gravitational influence of the giant planet that Enceladus orbits. The color of the tiger stripes in false color images reveals differences in composition and texture compared to the surrounding ice, appearing as blue-green stripes against the white of the surrounding terrain. This coloration indicates ice with different properties, perhaps ice that is cleaner, or ice with different crystal structure, or ice mixed with other materials from below. The false color images make the tiger stripes visually dramatic, highlighting their distinctive nature against the surrounding landscape. The naming of the tiger stripes after ancient cities adds a human touch to these geological features on a distant moon, connecting the familiar with the alien. Alexandria, Cairo, Baghdad, and Damascus, names that evoke history and human civilization, now also refer to fractures on Enceladus through which an alien ocean communicates with space. The naming convention follows established traditions in planetary science, using terrestrial references to designate extraterrestrial features. The presence of multiple parallel fractures suggests they share a common origin, formed by the same stresses acting on the ice shell of the Moon. The South Pole appears to be a region under particular stress, perhaps due to thinner ice or different internal structure, creating conditions favorable for fracturing. The parallel arrangement indicates a coherent stress field, forces acting in a consistent direction to create breaks in the ice oriented perpendicular to that force. The tiger stripes are symptoms of larger processes operating within Enceladus. The south polar location of the tiger stripes is not coincidental, as the South Pole appears to be a unique region on Enceladus, with properties distinct from the rest of the Moon. The ice shell is thinner here than elsewhere, allowing heat to escape more readily and fractures to penetrate more easily to the ocean below. The thermal and mechanical properties of this region make it the one place where the interior of Enceladus can communicate directly with space. Other regions of the Moon are sealed beneath thicker ice. The continuous activity along the tiger stripes means they are relatively stable features, not temporary cracks that will heal and close over geological time. The ongoing tidal forces that flex the moon with each orbit keep the fractures open and active, preventing them from freezing shut, even in the extreme cold. The heat from below also helps maintain the fractures, warm material keeping the ice along the walls from solidifying and sealing the passages. The tiger stripes are self-maintaining features. The visual appearance of the tiger stripes from the surface would be remarkable. Long, deep fractures cutting through the ice in parallel lines, stretching to the horizon in both directions. The walls would show the blue-green color of dense ice, descending into darkness below where warmer conditions exist, and where the ocean might be accessible. Vapor would rise from the fractures, crystallizing into ice particles as it met the cold vacuum above, creating the jets visible from space. Standing at the edge of a tiger stripe would be standing at the boundary between the surface world and the hidden ocean. The tiger stripes serve as conduits, connecting the frozen surface of Enceladus to something remarkable that lies beneath. A vast ocean of liquid water, completely encircling the moon below its icy shell. Beneath the frozen surface of Enceladus lies a global ocean of liquid water, a hidden sea that completely wraps around the moon under an ice shell that varies in thickness from place to place. This ocean is not a small pocket of melt or a temporary feature. It is a permanent, moon-spanning body of liquid water that has likely existed for millions or even billions of years. The water is kept liquid by heat from within the moon, warmth that prevents the ocean from freezing, despite the incredible cold of the outer solar system. The existence of this ocean was suspected from the plumes and confirmed through careful measurements of how Enceladus moves. The discovery of the global ocean came through studying the wobble of Enceladus as it orbits Saturn, a slight rocking motion called libration that reveals information about the moon's internal structure. If Enceladus were frozen solid all the way through, its wobble would be smaller, the entire moon moving as one rigid body. The observed wobble is larger than a solid moon should produce, indicating that the outer shell is separated from the core by a layer of liquid. The ice shell floats on an ocean, allowing it to wobble more freely than a solid moon could. The measurements that confirmed the ocean were made by precisely tracking Cassini's position during flybys and using those measurements to map the gravitational field of Enceladus in detail. The variations in gravity revealed the distribution of mass inside the moon, showing that the ice shell was indeed separate from the rocky interior. The data supported only one interpretation: a global ocean of liquid water lying between the ice above and the rock below. The hidden sea was real. The depth of the ocean is estimated to be somewhere between 10 and 30 kilometers, though the exact depth varies from place to place beneath the ice shell of differing thickness. This depth means the ocean contains an enormous volume of water, potentially more liquid water than exists on the surface of Earth in all our oceans combined. The scale is remarkable. This tiny moon, small enough to fit between major cities on Earth, harbors a hidden sea that rivals or exceeds Earth's ocean volume. The water is all below the ice, invisible to direct observation. The ice shell covering the ocean varies in thickness depending on location. Thinnest at the South Pole where the tiger stripes and plumes are located, and thickest near the equator and North Pole. At the South Pole, The shell may be only 20 to 25 kilometers thick, providing a relatively thin barrier between the ocean and space. Elsewhere, the ice may be 60 kilometers thick, or more, too thick for any fractures to penetrate completely through. The thinness of the South Polar ice explains why the plumes emerge exclusively from this region. The temperature of the ocean is thought to be close to the freezing point of water, which, at the pressures present at the ocean floor, is not exactly 0 degrees Celsius, but somewhere in that range. The water is kept liquid by the heat flowing from below, warmth generated in the rocky core that rises through the ocean and is eventually lost through the ice shell and the plumes. The ocean is not warm by human standards, but it is liquid, and liquid water is the key requirement that makes Enceladus so interesting. The darkness of the ocean is complete. No sunlight penetrating through the kilometers of ice that cover the liquid below. Any creatures living in this ocean would exist in total darkness, never experiencing light, except perhaps near any hydrothermal vents that might glow with their own heat. The darkness is shared by Earth's deep oceans, where thriving ecosystems exist far from sunlight, relying instead on chemical energy from the planet's interior. Darkness does not preclude life. The pressure at the bottom of the Enceladus ocean would be relatively moderate, less than the pressure in Earth's deepest trenches due to the Moon's weak gravity. An ocean 30 kilometers deep on Enceladus would produce roughly the same pressure as an ocean 3 kilometers deep on Earth. Significant, but not extreme by terrestrial standards. The pressures are within the range that Earth life can tolerate, and presumably within the range that any Enceladian life could tolerate as well. The salinity of the ocean has been determined through analysis of the Plume material, which contains sodium chloride and other salts that must have dissolved in the water below. The salt concentration appears similar to Earth's oceans, roughly 1 to 2% by weight, making the Enceladus Ocean a familiar-seeming environment in this respect. The presence of salt indicates that the water has been in contact with rock, dissolving minerals over time, a process that also provides the chemical ingredients that might support life. The connection between the ocean and the plumes is direct. The water erupting from the tiger stripes comes from this global sea, carrying with it information about conditions in the hidden depths. Each ice crystal in the plumes was once part of the ocean. Each salt grain was dissolved in the liquid below. Each organic molecule drifted in the dark waters before being carried up through the fractures. The plumes are samples of the ocean, delivered to space where our instruments can analyze them. The discovery of a global ocean on Enceladus expanded the category of places in our solar system that might harbor life, adding another entry to the list of ocean worlds that includes Europa and possibly several other icy moons. Before this discovery, the assumption was that liquid water required proximity to a star, warmth from sunlight, conditions found only in the inner solar system. Enceladus showed that internal heat could maintain liquid water far from any star, expanding the potential habitat for life throughout the cosmos. The age of the ocean is uncertain, but potentially very great, perhaps as old as the Moon itself, or nearly so. If the ocean has existed for billions of years, there has been ample time for chemistry to progress and for life to potentially emerge, assuming the other necessary conditions are present. The longevity of the ocean is important because life on Earth took hundreds of millions of years to appear after conditions became favorable, and similar timescales might apply elsewhere. The currents in the ocean are invisible to us, but must exist, driven by the heat entering from below and the cold ice shell above. Warm water would rise from the heated seafloor. Cool water would sink from the freezing interface with the ice shell. And this circulation would mix the ocean over time. The currents would distribute heat and nutrients throughout the liquid volume, creating a dynamic environment rather than a static body of water. The interface between the ocean and the ice shell above is a region of particular interest, where the freezing process continuously operates as heat is lost through the ice to space. Ice forms at this interface, growing downward as the ocean slowly freezes, while other processes, including tidal heating and warm plumes, prevent complete solidification. The balance between freezing and melting determines the thickness of the ice shell over time. The rocky core at the bottom of the ocean is where the most interesting chemistry may be occurring, where hot rock meets water and chemical reactions can proceed. On Earth, similar environments host hydrothermal vents that support rich ecosystems far from sunlight, raising possibilities about what might exist on the seafloor of Enceladus. The core is inaccessible to direct observation, but the chemistry of the plumes provides indirect evidence about what happens where rock and water meet. The hidden ocean of Enceladus is maintained by heat from within the moon, energy generated through a process connected to the gravitational influence of Saturn on this small world as it orbits the giant planet. The heat that keeps the ocean of Enceladus liquid comes from the flexing of the moon as it orbits Saturn, a process called tidal heating that converts gravitational energy into warmth deep inside the small world. Saturn's gravity is enormous, reaching out to grip all the moons that orbit around it, and this grip flexes and stretches each moon as it moves closer and farther from the planet in its orbit. The flexing generates friction inside the moon, and friction produces heat. The same way bending a paperclip back and forth warms the metal at the bend. Enceladus is continuously being kneaded by Saturn's gravity, and this kneading keeps its interior warm. The orbit of Enceladus is not perfectly circular, but slightly elliptical, meaning the moon moves closer to Saturn at some points in its orbit and farther away at others. This varying distance is crucial because it means Saturn's gravitational pull on Enceladus is constantly changing, stretching the moon more when it is closer and less when it is farther. The changing stretch produces continuous flexing, the moon alternately being squeezed and released as it orbits. This repeated flexing is what generates the internal heat. The amount of flexing depends on the shape of the orbit, and the orbit's shape is maintained by gravitational interactions with other moons in the Saturn system, particularly the moon Dione, which orbits farther out. Enceladus and Dione are in what astronomers call an orbital resonance, with Enceladus completing exactly 2 orbits for every 1 orbit that Dione completes. This resonance keeps Enceladus's orbit slightly elliptical rather than allowing it to become perfectly circular, ensuring the tidal heating continues indefinitely. The total heat produced by tidal heating in Enceladus has been measured at roughly 15 billion watts, a substantial amount of energy emerging from such a small moon. This heat is far more than can be explained by simple cooling from the moon's formation, which occurred billions of years ago and clearly indicates an active, ongoing energy source. The 15 billion watts emerges primarily through the South Polar region, escaping through the tiger stripes and the plumes in the form of warm water and heat radiation. The concentration of heat at the South Pole reflects the structure of Enceladus's interior, where tidal heating is most intense, in regions where the ice shell is thinner and where the geometry of the flexing focuses the energy. The South Pole has become a thermal hotspot, the primary outlet for the energy generated throughout the Moon's interior. This concentration is fortunate for exploration because it creates a single accessible region where the interior communicates with the exterior through the plumes. The mechanism of tidal heating is well understood in general terms, having been identified as the energy source for volcanic activity on Jupiter's moon Io and for the suspected ocean beneath Europa's ice. Io experiences such intense tidal heating that its surface is continuously reshaped by volcanic eruptions, the most volcanically active body in our solar system. Europa's heating is less intense, sufficient to maintain a liquid ocean, but not to produce dramatic surface volcanism. Enceladus falls between these extremes. The energy produced by tidal heating ultimately comes from the orbital motion of the moons around their host planet, gravitational energy being gradually converted to heat over cosmic timescales. This energy extraction slowly changes the orbits of the moons, though the changes are so slow that they are imperceptible over human timescales. The tidal heating will continue as long as the orbital resonances that maintain the elliptical orbits persist, which could be for billions of years more. The interior of Enceladus, where the tidal heating occurs, is inaccessible to direct observation, but models help scientists understand how the heat is generated and distributed. The rocky core experiences the most intense flexing and generates the most heat, which then flows outward through the ocean and eventually through the ice shell to space. The heat distribution creates temperature gradients that drive ocean currents and influence the thickness of the ice shell at different locations. The efficiency of tidal heating depends on the internal structure and composition of the Moon, with some materials dissipating energy more readily than others. The presence of liquid water in the interior actually enhances the heating by allowing more movement and friction than a completely solid interior would experience. The ocean is both a product and a contributor to the tidal heating process, a feedback loop that helps maintain the conditions favorable for liquid water. The comparison to familiar heat sources helps illustrate the scale of tidal heating on Enceladus. The 15 billion watts of heat is roughly equivalent to the output of 15 large nuclear power plants, emerging from a moon only 500 kilometers across. This energy density is remarkable for such a small world, and it reflects the intensity of the tidal forces acting on Enceladus due to its proximity to Saturn and its orbital resonance with Dione. The long-term sustainability of tidal heating ensures that the ocean of Enceladus is not a temporary feature destined to freeze, but a persistent environment that has likely existed for much of the Moon's history. As long as the orbital resonance with Dione persists, the heating will continue, and the ocean will remain liquid. The stability of the system means that any processes occurring in the ocean, chemical evolution, perhaps biological evolution, have had enormous spans of time to proceed. The seasonal variations in tidal heating occur on timescales of the orbital period around Saturn, roughly 33 hours for one complete orbit. During each orbit, Enceladus experiences stronger and weaker tidal forces as it moves closer to and farther from the planet, creating a rhythm of flexing that varies on a roughly daily timescale. The plumes have been observed to vary in intensity with this orbital rhythm, stronger at some points in the orbit and weaker at others. The generation of heat through tidal flexing represents one of the ways that gravity can drive geological activity on worlds far from any star, a mechanism that expands the potential for active worlds throughout the cosmos. Any moon in an eccentric orbit around a large planet can experience tidal heating, and many moons throughout our solar system and beyond likely maintain some internal heat through this mechanism. Enceladus is an extreme example, but probably not unique. The warmth generated by tidal heating is what ultimately drives the plumes, providing the energy to melt ice and vaporize water at the base of the tiger stripes, where the ocean meets the fracture system. Without tidal heating, the ocean would freeze, the fractures would seal, and the plumes would cease. The spectacular eruptions visible from space are powered by the gravitational energy of Saturn, converted through tidal flexing into the heat that maintains Enceladus as an active world. The heat that warms the ocean enables the chemistry that makes Enceladus so interesting for the search for life. And the plumes carry samples of that chemistry into space, where instruments can analyze what the ocean contains. The water erupting from Enceladus contains far more than just water itself, carrying along a complex mixture of dissolved and suspended materials that reveal the chemistry occurring in the hidden ocean below. When Cassini flew through the plumes with its instruments collecting samples, it found not only water vapor and ice crystals, but also salts, organic compounds, silica particles, and gases that speak to the conditions deep inside this small moon. Each component tells part of the story, helping scientists understand what the ocean is like and what processes are occurring at the seafloor. The presence of sodium chloride in the plumes, ordinary table salt, tells us that the ocean is salty, similar in this respect to Earth's oceans. The salt must have dissolved from rock over time, the water in contact with minerals in the seafloor and core, gradually acquiring the dissolved materials that now appear in the spray. The concentration of salt appears similar to Earth's seawater, making the Enceladus Ocean a broadly familiar-seeming environment, despite its exotic location in the outer solar system. Other salts are present as well, including potassium chloride and sodium carbonate, contributing to a complex brine that reflects the mineralogy of the rocks with which the water has interacted. These additional salts provide information about the types of rock present in Enceladus's core, suggesting a composition that includes materials similar to those found in certain types of Earth rock. The salt chemistry is a fingerprint of the geology hidden beneath the ocean, indirect evidence about the nature of the seafloor. The organic compounds detected in the plumes are among the most interesting components, carbon-containing molecules that are fundamental to life as we know it. Cassini's instruments detected molecules with masses suggesting complex organic chemistry, not just simple compounds like methane, but larger molecules with structures approaching biological relevance. The presence of these organics does not prove life exists in the ocean, but it demonstrates that the chemical building blocks for life are present in this environment. The complexity of some detected organic molecules exceeded initial expectations, with masses suggesting compounds in the same range as simple amino acids and other biologically important molecules. Later analysis found evidence for larger organics still, fragments of macromolecules that had apparently broken apart during the energetic process of eruption and collection. The chemistry in the ocean appears to be producing complex organics through processes we do not yet fully understand. The tiny silica particles found in the plumes provide particularly important information about conditions at the ocean floor, because silica of this specific type and size forms only under specific conditions. The particles are nanometer scale, far too small to see individually, and they form when hot water rich in dissolved silica encounters cooler water, causing the silica to precipitate out as tiny grains. This happens at hydrothermal vents on Earth, suggesting similar vents exist on the seafloor of Enceladus. The formation of these silica particles requires water temperatures of at least 90 degrees Celsius at the seafloor, much warmer than the bulk ocean temperature near freezing. This warmth indicates localized hotspots where water interacts with heated rock, the kind of environment that hosts thriving ecosystems on Earth. The silica is evidence of hydrothermal activity, active geology on the seafloor of Enceladus, producing conditions potentially favorable for life. The detection of molecular hydrogen in the plumes, announced in 2017 after extensive analysis of Cassini data, provided strong evidence for ongoing chemical reactions at the ocean floor. Hydrogen can be produced when water reacts with certain types of rock at high temperatures, a process called serpentinization that releases energy as well as hydrogen gas. On Earth, this reaction provides chemical energy for microorganisms living near hydrothermal vents, independent of sunlight. The significance of molecular hydrogen lies in its potential as an energy source for life. Microorganisms on Earth called methanogens combine hydrogen with carbon dioxide to produce methane and energy, living entirely on chemical reactions with no need for sunlight or oxygen. If similar organisms exist in the ocean of Enceladus, the hydrogen detected in the plumes could be feeding them. The chemistry creates the possibility of life without requiring sunlight to penetrate to the ocean. The carbon dioxide, also present in the plumes, would provide the carbon source that methanogens combine with hydrogen. And methane was detected as well, though whether it comes from biological or geological processes is unclear. The chemistry all fits together in a way that is consistent with a potentially habitable environment, the right ingredients present for the kind of life that thrives at hydrothermal vents on Earth. The pH of the ocean can be estimated from the chemistry of the plumes, and the evidence suggests the water is alkaline, with a pH around 8 or 9, similar to ammonia-bearing cleaning solutions. Alkaline conditions like these are found at certain hydrothermal systems on Earth and are thought to be favorable for some types of prebiotic chemistry, potentially providing conditions conducive to the origin of life. The overall picture emerging from the plume chemistry is of an active ocean in contact with a rocky seafloor, where hot water vents produce chemical gradients and release compounds including hydrogen that could serve as energy sources for life. All the ingredients known to be necessary for life as we know it appear to be present: liquid water, energy sources, organic compounds, and the right chemical conditions. This does not mean life exists, only that the conditions seem favorable. The analysis of plume material continued for years after Cassini's flybys, with scientists extracting more and more information from the data collected during those brief passages through the spray. Each new analysis revealed additional details about the ocean's chemistry, building a picture of an environment far more complex and potentially habitable than anyone had imagined before the plumes were discovered. The opportunity to analyze these samples came because Cassini was able to fly directly through the plumes, passing through the spray of material erupting from Enceladus and capturing particles and gas with its instruments. The Cassini spacecraft flew through the plumes of Enceladus multiple times during its mission, directly sampling the spray of water ice and vapor shooting from the south polar fractures into space. Each fly-through represented an extraordinary opportunity to collect material from an alien ocean without landing, without drilling, simply by passing through the spray at high speed and allowing the instruments to capture what they encountered along the way. The spacecraft carried instruments specifically designed to analyze the composition of particles and gases, tools that would reveal what secrets the ocean below held within its dark waters. The first dedicated Plume fly-through occurred in March of 2008, when Cassini passed just 52 kilometers above the surface of Enceladus, at the South Polar region. At that altitude, the spacecraft flew directly through the densest part of the spray, its instruments bathed in material fresh from the ocean hidden below. The passage happened at tremendous speed, roughly 8 kilometers per second, the spacecraft crossing the plume zone in a matter of seconds rather than minutes. Those few seconds of sampling would provide data that scientists would spend years carefully analyzing and interpreting. Flying through the plumes at such high speeds might seem dangerous, but the particles in the spray are tiny and widely spaced, posing no threat to the spacecraft. The ice crystals measure only about a micrometer across, far smaller than grains of sand, more like fine mist than threatening projectiles capable of causing damage. The spacecraft had been designed to survive the harsh environment around Saturn, including passages through various ring regions and near encounters with multiple moons. The Plume fly-throughs added something new to the mission's scope, an opportunity that had not been anticipated when Cassini was designed decades earlier. The spacecraft's ion and neutral mass spectrometer analyzed the gases in the plumes, determining what molecules were present and in what proportions they existed. This instrument could identify water vapor, carbon dioxide, methane, ammonia, and other substances by measuring the mass of individual molecules as they entered the detector. The data revealed that water vapor dominated the plumes, as expected, but also showed the presence of organic compounds and other materials that provided clues about conditions deep below. Each molecule detected told part of a larger story about the ocean and its chemistry. The Cosmic Dust Analyzer captured individual ice particles from the plumes, measuring their size, speed, composition, and electrical charge as they struck the detector. This instrument had been designed to study dust particles throughout the Saturn system, but it proved invaluable for understanding what the plumes contained beyond simple water ice. The analyzer revealed that some particles contained sodium chloride, ordinary table salt, indicating that the ocean below was salty like Earth's seas. Other particles contained silica, tiny grains that would prove enormously significant for understanding conditions on the ocean floor. Cassini conducted approximately 20 fly-throughs of the Enceladus plumes during its mission, each one at a different altitude or angle, building a comprehensive picture of the spray. Some passes skimmed close to the surface, flying through the densest parts of the plumes where material concentrations were highest for sampling purposes. Other passes occurred at higher altitudes, studying how the plumes spread and dispersed as they rose into space above the fractured South Pole. The variety of fly-through geometries allowed scientists to understand the three-dimensional structure of the eruptions and how they changed over time. The closest fly-through occurred in October of 2015, when Cassini passed just 25 kilometers above the surface of Enceladus, nearly skimming the tops of the geysers. At this altitude, the spacecraft was closer to the Moon's surface than commercial aircraft typically fly above Earth, though of course, there was no atmosphere to navigate through. The instruments captured their highest resolution data during this pass, detecting molecules and particles that might have been too sparse to detect at greater altitudes during previous encounters. This fly-through represented the most intimate contact possible without actually landing on the surface. The speed of the fly-throughs, while necessary for the orbital mechanics of the mission, did limit what could be detected during each brief passage. The spacecraft could not linger in the plumes, slowly sampling and analyzing, but instead had to gather data in quick passes, lasting only seconds each. The instruments were optimized for this kind of rapid sampling, designed to capture and analyze material quickly during the brief moments of plume immersion. Despite the time constraints, the accumulated data from multiple fly-throughs painted a detailed picture. The geometry of approaching Enceladus for a fly-through required careful navigation, with the spacecraft's trajectory planned months in advance to achieve the desired altitude and angle. Mission controllers on Earth sent commands that would execute during the fly-through itself, the spacecraft operating autonomously during the brief but critical sampling period. The distance between Earth and Saturn meant that real-time control was impossible, with signals taking over an hour to make the round trip between the two worlds. Every fly-through was essentially performed by the spacecraft on its own, following pre-programmed instructions. The sensation of flying through the plumes, if a spacecraft could feel such things, would have been subtle, the material so sparse that instruments rather than physical experience marked the passage. The plumes are visible in photographs because sunlight catches the ice particles, making them glow against the darkness of space. But the density is low enough that physical passage causes no resistance. The spacecraft moved through the spray like a hand through light fog, collecting samples that clung to instrument surfaces or passed through detector apertures designed to capture them. Each fly-through generated enormous amounts of data, too much to transmit to Earth immediately over the limited bandwidth available from Saturn's great distance. The data was stored aboard the spacecraft and transmitted gradually over days and weeks following each encounter. Scientists on Earth receiving the information in packets that slowly built into complete data sets. The analysis began while data was still arriving, with preliminary results sometimes announced within weeks, while deeper analysis continued for years afterward. The fly-through data revealed not just what the plumes contained, but also how the eruptions varied over time, and with Enceladus's position in its orbit around Saturn. The plume activity appeared stronger when Enceladus was further from Saturn in its slightly elliptical orbit, when tidal stresses opened the tiger stripe fractures wider and allowed more material to escape. This correlation confirmed the connection between tidal forces and the eruption mechanism, with Saturn's gravity directly controlling how much material escaped into space at any given time. The temperature of the plume material as it emerged from the fractures was measured during the fly-throughs, revealing that the vapor was warm compared to the surrounding ice surface. The warmth indicated that the material came from depth, from the ocean heated by tidal forces, rather than from surface ice that would be colder than the emerging spray. This temperature measurement added to the evidence that the plumes connected directly to the liquid ocean below, providing a conduit from the hidden sea to open space. The fly-throughs also allowed scientists to estimate how much material Enceladus was losing to space through the continuous eruptions from its south polar fractures. Roughly 200 kilograms of material escapes every second, a substantial mass loss that the small moon cannot sustain indefinitely without some replenishment or eventual depletion. This ejection rate means that the ocean is slowly losing water to space, though on timescales long enough that the process has likely continued for millions or billions of years without exhausting the supply. The data from the fly-throughs transformed our understanding of Enceladus from an interesting icy moon into one of the most compelling places in the solar system. Before these encounters, we knew the plumes existed and suspected an ocean below, but the fly-throughs provided direct chemical evidence about what the ocean contained and what processes might be occurring within it. The distinction between knowing something exists and understanding its composition is vast, and the fly-throughs bridged that gap for Enceladus's hidden ocean. The specific findings from these remarkable passages through the spray of an alien ocean would reshape our thinking about where life might exist beyond Earth. The data collected during Cassini's Plume fly-throughs revealed specific chemical signatures that transformed Enceladus from an interesting geological curiosity into a potential habitat for life as we understand it. The instruments captured detailed information about the ocean's composition, the processes occurring at the seafloor, and the conditions that might exist in the dark waters far below the frozen surface. Each discovery added another piece to a picture that grew increasingly compelling as the mission progressed through its years of observation. The detection of molecular hydrogen in the plumes, announced in 2017 near the end of Cassini's mission, represented one of the most significant findings about the ocean's chemistry. Hydrogen, in its molecular form, two hydrogen atoms bonded together, was present in the spray at concentrations suggesting active production somewhere in the system. This hydrogen could be produced by chemical reactions between hot water and rock, the same kind of reactions that occur at hydrothermal vents on Earth's ocean floor. The presence of molecular hydrogen indicated that chemical energy was available in the ocean, energy that could potentially support life. The process that produces this hydrogen is called serpentinization, a reaction that occurs when water meets certain types of iron-rich rock at elevated temperatures. The reaction transforms the rock chemically while releasing hydrogen as a byproduct, and this hydrogen carries energy that can be captured by certain types of microbes. On Earth, serpentinization at hydrothermal vents supports entire ecosystems of microorganisms that never see sunlight and derive all their energy from chemical reactions. The discovery of molecular hydrogen in the Enceladus plumes suggested that similar energy sources might exist on the seafloor. The amount of hydrogen detected was substantial enough to indicate ongoing production rather than ancient gas slowly leaking from rock that had reacted long ago. The measurements suggested that the seafloor of Enceladus was chemically active, with water continuously circulating through warm rock and emerging with hydrogen dissolved in it. This continuous production meant that energy was being continuously released, potentially available to support metabolic processes if any organisms existed to capture it. The hydrogen was a marker of activity, a sign that the ocean floor was not quiet and dead. The detection of silica particles in the plumes provided another crucial piece of evidence about conditions in the ocean, particularly at the boundary where water meets rock. These silica particles were tiny, only nanometers across, and they formed only under specific conditions that told scientists about the environment where they originated. Silica of this type forms when hot water saturated with dissolved silica encounters colder water, and the silica precipitates out as tiny grains. The presence of these particles indicated water temperatures of at least 90 degrees Celsius somewhere in the system. The temperature implied by the silica particles suggested that hydrothermal vents existed on the seafloor of Enceladus, places where hot water emerged from the rocky interior. On Earth, hydrothermal vents are oases of life in the deep ocean, supporting communities of organisms from microbes to tube worms to crabs. The warmth and the chemical energy available at vents create habitats independent of sunlight, ecosystems that could exist in any ocean with similar conditions. The silica particles were essentially a calling card from the seafloor, evidence of processes that on Earth are always associated with life. The organic compounds detected in the plumes added another layer to the habitability picture, revealing that the ocean contained carbon-based molecules that are the building blocks of life. The mass spectrometer detected complex organic molecules, with masses indicating they contained many atoms arranged in sophisticated structures. Some of these molecules had never been detected in space before, their presence suggesting chemical complexity beyond simple compounds like methane and carbon dioxide. The ocean of Enceladus was not just water. It was a chemical environment with ingredients that life requires. The specific organic molecules detected included nitrogen-containing compounds and oxygen-containing compounds, both important for biology as we understand it on Earth. The masses of some molecules suggested they could be amino acids or similar structures, though the instruments could not definitively identify specific compounds at such complexity levels. The ambiguity was frustrating, but also tantalizing, because the data was consistent with what we might expect to find if biology were present, without conclusively proving such presence. The salt content of the ocean, revealed through analysis of particles containing sodium chloride, indicated that the water had been in contact with rock for extended periods. Salt enters ocean water through the dissolution of minerals from rock, a process that takes time and requires water-rock interaction. The salinity, measured in the plume particles, was similar to Earth's oceans, suggesting that Enceladus's ocean had achieved a chemical equilibrium with its rocky floor over geological timescales. The ocean was not freshwater, but a salty sea, perhaps more similar to our own oceans than to a freshwater lake. The pH of the ocean, estimated from the chemical data, appeared to be alkaline, perhaps around 9 on the pH scale, somewhat higher than Earth's oceans, but within a range compatible with life. Alkaline conditions are actually favorable for certain types of chemistry relevant to life's origins, and some scientists have suggested that life on Earth may have originated in alkaline hydrothermal environments. The Enceladus Ocean's chemistry fell within ranges that seemed hospitable rather than hostile to biology as we understand it. The combination of findings, liquid water, chemical energy from serpentinization, organic compounds, appropriate pH, sustained conditions over geological time, created a picture of an environment that met all the basic requirements we know of for life. This did not prove that life existed, only that the conditions necessary for life appeared to be present in the hidden ocean. The distinction is important but also remarkable, because we had not expected to find such favorable conditions on a small moon so far from the Sun. The flythroughs also revealed how the plume activity varied over time, and with the moon's orbital position showing that the eruptions were controlled by tidal forces. When Enceladus moved farther from Saturn in its slightly elliptical orbit, the tiger stripe fractures opened wider and more material escaped. When the moon moved closer to Saturn, the fractures compressed slightly and the flow diminished. This rhythmic variation confirmed the mechanical connection between orbital dynamics and geological activity. The data suggested that the ocean might circulate, with heated water rising from the seafloor and mixing with cooler water near the ice shell above. This circulation would distribute heat and chemicals throughout the ocean, potentially creating conditions where life could thrive rather than being confined to isolated hotspots. The dynamics of the ocean remained poorly understood, limited by how much could be inferred from sampling material that had traveled from the seafloor, through the ocean, through fractures into space. The cumulative picture from all the flythroughs showed an ocean that was chemically active, thermally active, and connected to the surface through fractures that allowed sampling without landing. No other world in the solar system offered such convenient access to a subsurface ocean. The ability to study what lay below without drilling through kilometers of ice. The plumes were windows into the ocean, and Cassini had looked through those windows during every fly-through. The findings raised questions about whether life might have arisen independently in this distant ocean, questions that the Cassini mission could not answer definitively. The question of whether life might exist in the ocean of Enceladus became one of the most compelling inquiries in astrobiology, following the discoveries made by Cassini's instruments during the Plume. Fly-throughs, the combination of liquid water, chemical energy, organic compounds, and stable conditions over geological time, created an environment that met all the basic requirements we know of for life as it exists on Earth. This did not prove that life existed, but it established that the necessary conditions appeared to be present in this small moon's hidden ocean, far from the warmth of the sun. Life on Earth requires liquid water, and Enceladus has a global ocean of liquid water that has likely existed for billions of years beneath the protective ice shell. Life requires energy, and Enceladus has chemical energy available from the reactions between hot water and rock at hydrothermal vents on the ocean floor. Life requires organic compounds as building blocks, and Enceladus has complex organic molecules detected in the plumes spraying from the south polar fractures. Life requires time to emerge and evolve, and the ocean has apparently persisted for geological eons. The hydrothermal vent environments suggested by the silica particles and molecular hydrogen detected in the plumes are particularly significant for thinking about potential life. On Earth, hydrothermal vents support thriving ecosystems in the deepest, darkest parts of the ocean, completely independent of sunlight and the photosynthesis that powers most surface life. These vent communities derive their energy from chemical reactions, the same serpentinization and related processes that appear to be occurring on the seafloor of Enceladus. The parallel is striking and suggestive. Some scientists believe that life on Earth may have originated at hydrothermal vents, where the combination of chemical energy, warm water, mineral surfaces, and organic compounds created conditions favorable for the emergence of the first living cells. If life began at hydrothermal vents on Earth, then similar environments on other worlds might also give rise to life independently. Enceladus appears to have exactly this kind of environment, hidden beneath its ice, but connected to space through the remarkable plumes that Cassini flew through repeatedly. The accessibility of the Enceladus Ocean through the plumes makes this moon unique among the potentially habitable worlds in our solar system. Europa, Jupiter's moon, also likely has a subsurface ocean, but that ocean is sealed beneath many kilometers of ice, with no known plumes providing natural samples. Enceladus offers something extraordinary. The ocean material shoots into space continuously, free for the taking by any spacecraft equipped to sample it. A future mission would not need to land and drill, but could simply fly through the spray. The organic compounds detected in the plumes are consistent with what we might expect to find if microbial life existed in the ocean. But they are also consistent with purely abiotic chemistry. This ambiguity is frustrating for those hoping for a definitive answer, but it also reflects the genuine difficulty of distinguishing life signatures from those of non-living chemistry. The molecules that life uses are made of the same atoms arranged in similar ways to molecules that form without life's involvement. The search for biosignatures, chemical or structural evidence of life, requires looking for patterns that life produces, but chemistry alone typically does not. Certain ratios of isotopes, specific arrangements of molecules, particular types of structures visible under microscopes, these are the signs that might reveal whether life exists in the dark waters of Enceladus. Cassini's instruments were not designed to search for life, and could not perform the detailed analyses needed to detect unambiguous biosignatures. That task awaits future missions. The possibility that life might exist in the Enceladus Ocean does not mean that life definitely exists there, a distinction that scientists are careful to maintain. The conditions appear favorable, the ingredients appear present, but favorable conditions do not guarantee that life will emerge. Life might require something we do not yet understand, some factor absent from Enceladus, despite the promising chemistry. Or life might be there, thriving in the darkness, utterly unaware that anything exists beyond the ice above. If life does exist in the Enceladus Ocean, it would represent a second independent origin of life in our solar system, evidence that life is not a fluke, unique to Earth. The implications would be profound for understanding our place in the universe, suggesting that life arises readily wherever conditions permit, rather than being a rare accident. Two origins in one solar system would strongly suggest that life is common throughout the universe, that countless worlds harbor living things in their oceans and atmospheres. The characteristics of any life in the Enceladus Ocean would likely be unfamiliar, even while sharing some fundamental biochemistry with Earth life. If our understanding of chemistry is correct, life there would have evolved independently for billions of years, in complete isolation, developing in an environment utterly unlike Earth's sunlit surface. The organisms might be entirely different in appearance and metabolism, while still using the same basic molecular machinery that chemistry favors. Or they might be truly alien in ways we cannot predict. The dark environment of the Enceladus Ocean would mean that any life there never experienced light, evolving entirely in perpetual darkness, warmed by hydrothermal heat from below. Such life would have no concept of vision, no eyes, no colors, only whatever senses proved useful for navigating a world of water and rock and warm vents. The silence and darkness of this ocean stretches to depths we can barely imagine, a world defined by chemistry and temperature rather than the light that dominates Earth's ecosystems. The scale of the Enceladus ocean means that even if life was sparse, the total amount might be substantial across the entire volume of liquid water beneath the ice shell. A few microbes per liter spread across an ocean potentially deeper and more voluminous than Earth's surface waters would represent an enormous amount of life in absolute terms. We cannot know how densely populated the ocean might be, but the possibility of even sparse microbial life is remarkable when considering a world so far from the sun. The patience required to search for life in such a distant ocean reflects the nature of the question itself, one of the deepest questions humans have ever asked about the universe we inhabit. We wonder if we are alone, if life on Earth is unique or common, if the cosmos teems with living things or sits empty except for our small blue world. Enceladus offers an opportunity to answer this question, a world where the necessary ingredients appear present and where samples are accessible through the remarkable plumes. The material erupting from Enceladus does more than offer samples of the ocean below. It creates a visible feature that spreads far beyond the small moon itself. The material shooting from Enceladus into space does not simply fall back to the surface or dissipate into nothingness, but instead spreads outward to form Saturn's largest ring, a vast structure called the E-ring that encircles the planet. This connection between a tiny moon and an enormous ring feature was suspected before Cassini confirmed it. But the mission's observations demonstrated conclusively that Enceladus is the source of the particles that comprise this diffuse outer ring. The moon is continuously feeding material into space, and that material spreads to form a structure visible across millions of kilometers. The E-ring stretches from the orbit of Mimas, one of Saturn's inner moons, all the way out beyond the orbit of Titan, the planet's largest moon. This enormous extent makes the E-ring the most expansive of Saturn's many rings, though it is also the most diffuse and hardest to see directly. Unlike the brilliant main rings composed of larger chunks of ice reflecting sunlight intensely, the E-ring consists of microscopic particles that scatter light more subtly. The ring is visible primarily when viewed from angles where the tiny particles catch and scatter incoming sunlight. Enceladus orbits at the heart of the E-ring, precisely at the location where the ring is densest and brightest in the observations that reveal its structure. This positioning is not coincidence, but causation. The ring is densest here because this is where the source material originates, where the plumes inject fresh ice particles into the surrounding space. The particles spread both inward towards Saturn and outward away from the planet, eventually populating the full extent of the ring through orbital dynamics that slowly disperse them over time. The particles in the E-ring are tiny, typically about 1 micrometer in diameter, far smaller than grains of sand or even particles of dust visible to the human eye. These microscopic ice crystals are about the size of bacteria, small enough that they are affected not just by gravity, but also by radiation pressure from the sun and electrical forces from Saturn's magnetic field. Their small size explains both why they spread so widely and why they remained suspended in the ring, rather than quickly falling towards Saturn or escaping to interplanetary space. The rate at which Enceladus supplies material to the E-ring has been measured through observations of the plumes and the ring itself, providing an estimate of roughly 200 kilograms per second. This continuous injection of fresh material is necessary because the ring particles are gradually lost through various processes, including collisions with other moons, incorporation into Saturn's atmosphere, and ejection from the system. Without constant replenishment from Enceladus, the E-ring would fade away over astronomical timescales. The E-ring is essentially a spray of Enceladus material spread around Saturn's orbit, a three-dimensional structure populated by particles that originated in the ocean of a small icy moon. Some of these particles have traveled from the seafloor through the ocean, through fractures into space, and now orbit the giant planet as part of its ring system. The connection is remarkable. Ocean material from a tiny moon forming a structure visible across millions of kilometers of space, surrounding one of the largest planets in our solar system. The discovery that Enceladus feeds the E-ring came before the full understanding of the plumes themselves, providing early evidence that the small moon was somehow active. Astronomers had noticed that the E-ring was brightest at the orbit of Enceladus and had hypothesized that the moon must be supplying material, though the mechanism was not initially understood. The discovery of the plumes provided the explanation. The moon was literally shooting its ocean into space, and that ejected material was becoming the ring. Other moons orbit within the E-ring, passing through the material that Enceladus supplies, their surfaces gradually coated by the falling particles over geological time. These moons appear slightly brighter and fresher than they would otherwise because they are continuously dusted with new material from Enceladus's plumes. The E-ring is not just a static structure, but an active environment where particles move and interact and fall onto surfaces throughout its enormous extent. The composition of the E-ring particles matches what Cassini detected in the plumes directly, confirming the connection between the eruptions and the ring structure. The particles contain water ice primarily, but also traces of the other materials present in the plumes, including salt and organic compounds carried from the ocean below. The ring is essentially an extension of the ocean, its composition reflecting what lies beneath the ice of the source moon. The lifetime of individual particles in the E-ring varies depending on their orbits and their interactions with other objects and forces. The typical particles might survive for decades to centuries before being lost. This means the ring we see today contains particles ejected recently in geological terms, material that left Enceladus within the past few hundred years at most. The ring is fresh, constantly renewed, a dynamic feature rather than an ancient relic. The visual appearance of the E-ring depends strongly on viewing geometry, becoming most visible when the sun illuminates the particles from behind and they scatter light toward the observer. In these backlit images, the ring appears as a faint glow surrounding Saturn, distinct from the brighter main rings that appear best in direct illumination. Cassini captured numerous images of the E-ring from various angles, revealing its structure and confirming its connection to the plumes. The existence of the E-ring means that Enceladus has been active for a long time, continuously supplying material at a rate sufficient to maintain the ring structure against the losses that would otherwise deplete it. If the plumes were a recent phenomenon, the ring would not yet have reached its current extent and density. The ring's presence suggests that Enceladus has been erupting for at least millions of years, maintaining its output throughout this extended period of geological activity. The connection between a hidden ocean, erupting plumes, and a planetary ring system represents one of the most remarkable linkages discovered in our exploration of the outer solar system. A tiny moon's internal ocean provides material that ends up orbiting the giant planet as part of its ring structure, a connection spanning scales from the microscopic ice particles to the millions of kilometers of the ring's full extent. The discoveries made at Enceladus have inspired scientists to propose future missions that might return to this remarkable moon with instruments specifically designed to search for signs of life. The remarkable findings about Enceladus from the Cassini mission have generated substantial scientific interest in returning to this small moon with dedicated instruments capable of searching for signs of life. Several mission concepts have been proposed and studied, each designed to take advantage of the unique accessibility that the plumes provide to the hidden ocean below. These proposed missions range from simple fly-throughs with advanced instruments to ambitious landers that would touch down near the tiger stripe fractures. The Enceladus Life Finder, known by its initials as ELF, was one of the first serious proposals for a dedicated mission to search for biosignatures in the plumes. This concept envisioned a spacecraft that would fly through the plumes multiple times, carrying instruments far more capable than those aboard Cassini for detecting signs of life. The key instruments would include advanced mass spectrometers able to identify specific organic molecules that life produces, potentially resolving the ambiguity that Cassini's measurements left regarding the nature of the organic compounds detected. The search for amino acids would be a primary goal of any life detection mission to Enceladus, since these molecules are the building blocks of proteins and are strongly associated with life as we know it. Cassini detected organic molecules with masses consistent with amino acids, but the instruments could not definitively identify whether amino acids were actually present in the plumes. A future mission with more capable instruments could resolve this question, determining whether the ocean contains these life-essential molecules in forms suggesting biological origin. Beyond simply detecting amino acids, future instruments could analyze their chirality, the handedness of their molecular structure that differs between biological and non-biological sources. Life on Earth uses almost exclusively left-handed amino acids, a preference that appears to be arbitrary but is consistent across all known terrestrial life. Finding predominantly one-handed amino acids in the Enceladus plumes would be strong evidence of biological origin, since non-biological chemistry typically produces equal mixtures of both handedness types. The Enceladus Orbilander concept proposed by scientists represents a more ambitious approach, combining an orbiting phase with an eventual landing on the surface near the plume sources. The spacecraft would first orbit Enceladus, studying the plumes from multiple angles and altitudes, then eventually descend to the surface to sample material directly. Landing would provide access to plume fallback material, the particles that rise from the fractures, but do not achieve escape velocity and fall back as snow onto the surrounding terrain. A lander near the tiger stripes could potentially sample material more concentrated than what is available in the dispersed plumes higher above the surface. The fallback snow has been accumulating for millions of years in some areas, creating deposits that might be analyzed for signs of life with instruments similar to those used for biological detection on Earth. The challenges of landing on Enceladus include the extreme cold, the distance from Earth limiting communication, and the need for a power source that functions in the dim light so far from the Sun. Some proposals have envisioned even more ambitious approaches, including missions that would land directly on the tiger stripes and potentially lower instruments into the fractures themselves. These concepts push the boundaries of current technology, but represent the kind of exploration that might eventually be necessary to definitively answer questions about life in the Enceladus ocean. The fractures themselves might provide access to material fresher and more representative of the ocean than anything available at the surface. The search for lipid membranes represents another promising approach for life detection, since all known life uses membrane structures to separate the interior of cells from the external environment. Cassini detected hints of complex organic molecules that could potentially be lipids, but definitive identification was not possible with the instruments available during that mission. Future missions could carry instruments designed specifically to identify membrane-forming molecules in the Plume samples. Microscopy represents a direct approach to life detection that could potentially image intact cells or cell fragments if they are present in the plumes. A sufficiently capable microscope aboard a future mission could examine plume particles for structures consistent with cellular life, small packets of organic material enclosed by membranes. This direct observation would provide compelling evidence that would complement the chemical analyses performed by other instruments. The time required for a mission to reach Enceladus presents a practical challenge for mission planning, with travel times to Saturn typically requiring 7 years or more using current technology. The distance means that any mission must be highly reliable, capable of operating for extended periods before reaching its target, then functioning in the harsh environment around Saturn for years of scientific observations. The investment required is substantial, motivating careful consideration of mission designs and scientific goals. The funding landscape for such missions remains uncertain, with competition from other compelling destinations, including Europa, Mars, and Titan, for limited resources available for planetary exploration. Enceladus advocates argue that the accessibility of the ocean through the plumes makes this moon uniquely valuable, providing the opportunity to sample a subsurface ocean without the complexity of drilling that Europa would require. The scientific community continues to discuss and debate which destinations offer the best chances for transformative discoveries. The development of instruments capable of detecting life in the challenging conditions of a plume fly-through or surface landing continues to advance, with laboratory work improving the sensitivity and specificity of detection methods. Each advance in instrumentation makes a future mission more capable of answering the fundamental questions about whether life exists in the Enceladus ocean. The technology improves even as the decisions about which missions to pursue work through the long planning processes of space agencies. Whether any of the proposed missions will eventually fly remains to be seen, dependent on the priorities of space agencies, the availability of funding, and the continued advocacy of scientists who believe Enceladus represents one of the best opportunities for discovering life beyond Earth. The vision of returning to this tiny moon, with instruments designed specifically to search for life, continues to inspire the scientific community and the public alike. Regardless of what future missions might discover, Enceladus has already changed our understanding of where habitable environments might exist throughout the cosmos. The small moon Enceladus continues to orbit Saturn, its plumes erupting continuously from the tiger stripe fractures at its south pole. Water from a hidden ocean shooting into space, whether or not anyone observes it. The geysers have been active for millions of years and will likely continue for millions more. A persistent feature of this remarkable world that transformed our understanding of what is possible in the cold outer reaches of our solar system. The moon is tiny by any standard, small enough to fit within a medium-sized country on Earth. Yet, it contains a global ocean that may hold more liquid water than all the seas and lakes and rivers on our own planet. Before the Cassini mission revealed what was happening at Enceladus, scientists did not expect to find geological activity on such a small world so far from the sun. The moon was thought too small to retain internal heat, too cold to harbor liquid water, too distant from any energy source to drive active processes. The discovery of the plumes shattered these assumptions, demonstrating that the universe contains possibilities beyond what our limited experience had led us to expect. The lesson of Enceladus is humility about our predictions. The ice shell that covers Enceladus gleams bright white, one of the most reflective surfaces in the solar system, constantly renewed by material falling from the plumes above. The brightness comes from fresh ice, snow that has fallen from the geysers over millions of years, covering whatever older terrain once existed beneath. The South Polar region is particularly fresh, relatively free of craters because impacts have been buried by the continuous deposition of plume fallback. The surface tells its own story of activity. The tiger stripe fractures stretch across the South Polar terrain, 4 roughly parallel lines that serve as the conduits connecting the hidden ocean to open space. These fractures are living features, opening and closing with the tidal rhythms of Enceladus's orbit around Saturn, breathing in and out as the moon is squeezed and released by the giant planet's gravity. The geysers emerge from specific points along these fractures, over 100 individual jets, identified in the careful imaging performed by Cassini during its many years of observation. The ocean below remains largely mysterious, despite everything we have learned through the plume samples and the careful analysis of the moon's orbital behavior. We know the ocean exists, encircling the moon beneath ice that varies from perhaps 20 kilometers thick at the South Pole to 60 kilometers or more elsewhere. We know the water is salty and contains organic compounds and shows signs of hydrothermal activity on the sea floor. But we do not know what the ocean actually looks like, what currents flow through it, what might live in its dark waters. The hydrothermal vents suggested by the silica particles and molecular hydrogen detected in the plumes represent environments similar to those that support thriving ecosystems in Earth's deepest oceans. On our world, these vents are islands of warmth and chemistry. In an otherwise cold and dark abyss, places where life flourishes, independent of sunlight and photosynthesis. Whether similar communities exist around vents on the Enceladus seafloor remains unknown, a question that awaits future exploration with instruments designed to search for signs of biology. The connection between the ocean and the surface through the plumes makes Enceladus unique among the potentially habitable worlds of our solar system. Europa almost certainly has an ocean beneath its ice, but that ocean is sealed away without known plumes providing samples. Titan has lakes of liquid methane on its surface, but these are fundamentally different from the water ocean of Enceladus. Only here do we have a subsurface water ocean that actively exposes its contents to space, offering samples for the taking by any spacecraft that flies through the spray. The E-ring that Enceladus creates extends far beyond the Moon itself, spreading particles from the ocean across millions of kilometers around Saturn. This ring is perhaps the only planetary ring in our solar system that we understand completely, knowing exactly where its particles come from and why it exists. The ring is fed by the plumes, which are fed by the ocean, which is maintained by tidal heating from Saturn. The chain of causation connects the giant planet to its tiny moon, to the ring that encircles them both. The scientific legacy of Enceladus extends beyond the specific findings about this one moon to broader questions about where life might exist throughout the universe. If a small, icy moon can harbor an ocean and hydrothermal vents and organic chemistry, then perhaps similar environments exist on countless worlds around other stars. The icy moons of our solar system may be typical rather than exceptional, suggesting that habitable environments are far more common than we once assumed. The search for life beyond Earth has focused historically on planets in the habitable zones of their stars, worlds where liquid water might exist on the surface under the warming influence of stellar radiation. Enceladus demonstrates that habitable environments can exist far beyond these zones, in places where internal heat, rather than starlight, maintains liquid water. The universe of potentially habitable worlds is larger than we thought, encompassing not just planets warmed by their stars, but moons warmed by the gravitational tides of the giant planets they orbit. The questions raised by Enceladus may take decades to answer, requiring future missions with advanced instruments to determine whether life actually exists in this hidden ocean. The process of science is slow, particularly when the target is billions of kilometers away and the questions are among the most profound that humans have ever asked. Whether we are alone in the universe, whether life arises wherever conditions permit, whether biology is common or rare, these questions drive the continued interest in Enceladus and the proposals for missions to return. The small moon orbits Saturn in silence, its plumes rising against the darkness of space, visible in sunlight as ghostly sprays emerging from fractures in the ice. The geysers do not know that they have been observed, that their contents have been sampled and analyzed, that their existence has inspired wonder and scientific inquiry on a distant planet called Earth. The eruptions continue because physics demands that they continue. The tidal squeezing driving warm water through fractures into vacuum, where it explodes into vapor and ice. Whatever exists in the ocean of Enceladus, whether living or not, remains patient in the darkness beneath the ice, waiting for nothing because it cannot wait. The water is there, the chemistry is there, the time has been there for billions of years. If life exists in these waters, it has evolved without any awareness of the universe beyond its frozen ceiling. If life does not exist, the ocean remains remarkable simply for being. Liquid water maintained in the outer solar system by the gentle squeezing of gravitational tides. The night sky that contains Saturn also contains Enceladus, though the tiny moon is far too small and distant to see with unaided eyes from Earth. But knowing it exists changes what we see when we look toward that region of the sky, transforms a point of light into a system containing worlds where water erupts into space from hidden oceans. The universe has revealed something remarkable at this small moon. something that enriches our understanding of what is possible in the cosmos we inhabit together.